Good afternoon, everybody. It's a pleasure to be here and have the opportunity to give a plenary talk on semiconductor disc lasers and Sesam. So this work has been ongoing over many generations of PhD students who are shown here. And it only has become possible because of the access to MBE growth at ETH in the first lab and long-term MBE grower with Dr. Matthias Golling and the long-term funding. This is the effort that has been concentrating in the near infrared, mostly based on indium gallium arsenide GaN medium. And I recently started an effort to push this technology into the long wavelength, the longer than 2 micrometer, with the funding of a ERC grant. And we hired an additional grower that is supporting it. And this basically shows the team that got this one going. And I'm very happy to show you some of the first positive results that we got out of this work. So this is the outline of my talk. So I first will give you a first introduction on the basic device structure and also show you some of the application demonstrations. Then make some discussion about the material optimization that we have been doing in the near infrared and the whole device mixel and Sesam optimization for the near infrared. And then, as I said, I'll show you the initial results, initially the Sesam and outlook. So let's get started. So when you passively mode lock a laser, you have a gain element in the laser cavity here and a loss element. So you can do active mode locking, then you have acousto-optic modulator, which is typically a sinusoidal loss modulation. And that one opens up a net gain window which supports the short pulses for 1 pulse per cavity round trip. So you can replace this loss modulator by a saturable absorber, for example, a semiconductor saturable absorber, which is integrated with a high reflecting mirror. So you have the loss directly on a high reflector mirror. So this is the end mirror of your linear laser cavity. And the advantage with the saturable absorber is that you can get a self-amplitude modulation, which has a much stronger curvature and therefore opens up a shorter net gain window that also supports short pulses. The whole thing starts when every parameter is adjusted right out of normal noise fluctuation. In the near infrared, the loss modulation was obtained with band filling. So you have basically, as here is shown, a bulk semiconductor, which valence band and the conduction band as a function of energy. So you have the photon, you take the electron from the valence band to the conduction band within the bandwidth of your pulse, and that occupies the states and therefore reduces the losses initially. Because of band filling, Pauli exclusion principle, the states are filled. And then they thermalize within the conduction band, depending on where you actually excite this electron. And that gives you initial recovery of the absorption bleaching, because you have less electrons in the states that are recovered by the bandwidth of the pulse. And then ultimately you have the recombination of the electrons with the valence. And this recombination in a good semiconductor normally is in the nanoseconds. And however, we need a faster saturable absorber, as I will show you then. And that basically means you can introduce so-called mid-gap traps in a very controlled fashion by low temperature growth to then reduce the recovery time. When you do everything right, you end up with a massive, just a nonlinear mirror that goes into the laser cavity, and you get short pulses. And that replaced these acousto-optic mode lockers that have been using for solid-state laser, which need RF power and water cooling. and was so much simpler and gave better performance, and that was simply successful. So today, in all commercial lasers, the Sesam is doing the mode locking. Now, when you look at the gain medium, we initially focused our work on dipole solid-state lasers, and when you look at the gain cross-section, it's typically in the 10 to minus 19, 10 to minus 20, or even smaller. And if you compare that to the semiconductor or the dye laser, there is orders of magnitude difference, and that has an effect on the mode locking physics. So when you have the really small gain cross-section, which is typical for ion doped solid-state laser, you actually, even if you have short pulses, you have only a constant gain saturation. So you have a gain saturation based on the CW power of the laser. And initially, it was assumed that you need to have a fast saturable absorber to open up a net gain window, but then we showed over time that this is not the case. If you have a significant solid-on pulse shaping, you actually can have a much more relaxed saturable absorber parameter. It can be quite longer, with a longer net gain window, still get very high quality short pulses, because the absorber is only starting and stabilizing solid-on mode locking, but the pulse formation, the final pulse formation, is dominated by the solid-on formation. This is different in the semiconductor. So because we have a much larger gain cross-section, if you have pulses in the laser cavity, then you have a significant dynamic gain saturation, and you actually need to adjust the loss and the gain parameters more carefully to maintain the short pulses and get stable passive mode locking. When you choose a semiconductor as a gain medium, we basically use the semiconductor here shown green with quantum well gain in a vertical configuration. And I'll explain why. Because if you integrate it in the vertical, so you have basically a diode pumped semiconductor structure, which is a high reflector with the quantum well and an air coating. So the laser cavity is formed by this chip, semiconductor chip, and an external cavity. So this chip is in the order of 10 micrometer, whereas the external cavity in centimeters. And this is called a so-called vertical external cavity surface emitting laser. You have lower gain because you go vertical to the quantum well, and therefore you only have a low output coupler, which means you have a high Q cavity and also low noise, which I can show you later on. The external cavity, it gives you real advantage because you can put additional elements in it. Because you have a high Q cavity, you have a much higher intensity inside the cavity. So you can put a Sesam into it to do mode locking, and you get nice clean mode conversion if you pump with a lower quality pump laser. In comparison to dipole solid-state laser, the semiconductor laser gain medium offers you bandgap engineering, so you have much more flexibility in the exact wavelengths of operation. You have a higher level of integration, you have a wafer scale technology, and you can scale this semiconductor in power. The key is, when you have your gain structure, your semiconductor optically pumped semiconductor chip, VCSEL chip here, and you have your external output coupler. The gain chip is only 10 micrometer thick, so you can scale the power by opening up the mode size on the gain chip, and power up to 100 watt has been demonstrated. You can then mode lock. It's very similar to dipole solid-state lasers. We just added an additional element in the cavity. So we have a Sesam as an end mirror, the gain, and then the output coupler in this V-shaped cavity design. And if all the parameters are adjusted right, we get stable passive mode locking. This was initially demonstrated in 2000 with a collaboration between Antropper and me, and that was actually one of the early reviews that we published with this work. Now, because we have with this passively mode locked VCSEL, a gain material that is based on semiconductor, and a saturable absorber that is based on semiconductor. So we can integrate the whole thing into one single wafer, which we call then the MIXL, the mode-locked integrated external cavity surface emitting laser, following the VEXEL, the cell type of acronym. And here the MIXL chip contains both the gain and the saturable absorber. And we introduced an intermediate highly reflecting mirror that reflects the pump so that the pump light is not starting to saturate the absorber. And if everything is adjusted right, you pump CW and get perfect mode lock pulses out of this laser. And as I said, with the, for example, a cavity length of about 5 centimeters, you get a 3 gigahertz pulse repetition rate with only one pulse circulating inside the cavity. Because you have an extra cavity, you can also put in an ethanol to get a tunable, or without the ethanol, there are different options here. So let me just briefly, before I go into the material optimization, the application demonstrating without going too much into the details. We invented the dual comb mode locking by introducing an intracavity birefringent crystal inside the cavity that gives then two possible modes which are separated inside a laser cavity through the polarization. So it's polarization duplexing. And they hit the mixel, which is the same. You keep the distance so that they don't overlap, and you get two spatially separated beams, which are basically experience the same gain and also the saturable absorber. So you get two mode-locked pulse frames with a little bit of a different pulse repetition rate because they have the different refractive index in the birefringent crystal, the ordinary refractive index, ordinary refractive index. And that gives you a different optical path length and a different pulse repetition rate of the mode-locked pulse frame, which is actually favorable for dual comb application. And you have a mutual stability. So all the applications that we did was actually work with a free running laser. So you don't need to stabilize two mode-locked lasers to do dual comb. So the first time we demonstrated that was with a dual comb mixel operating at 968 nanometer. There is a little bit of water absorption, and so we showed water spectroscopy at this wavelength in taking this dual comb mixel and sending both combs through the multipath cell and another one to the reference. And that gives you the two mode locked spectrum. And one has then the absorption in the water, which you see by eye. And if you take the difference between the two, you actually end up with the spectral absorption of the water wave. And this measurement is extremely fast. So if the pulse repetition rate is difference is 1 kilohertz, you can make a measurement in 1 millisecond. That's actually the power of the dual comb spectroscopy application. We then also did another mixel at 1 micron, 1.03 micron, with actually femtosecond pulses, and so that we had an overlap with the absorption cross-section of acetylene. And we could also successfully demonstrate dual comb spectroscopy in this regime, even though the spectral overlap wasn't perfect, but we could basically correctly see the absorption line of acetylene. We did that work in collaboration with Nathalie Piquet and a commercial multipath cell to do this demonstration. Then we also used the mixel for LiDAR application. So here we actually compare both a dual comb mixel, which is an optically pumped semiconductor, and the dual comb solid state laser at a lower repetition rate, 136 megahertz, versus the mixel was at 2.7 gigahertz. They were operated both in the 1 micrometer regime and had similar performance. I mean, this one had the mixel had 390 femtosecond and the diatom solid state laser 175 femtosecond pulses. And we had a here of 51 kilohertz and here 90, 50 952 hertz. We had a ambiguity range, which is given by the pulse repetition rate. So we use the gigahertz, have 55 millimeter, and at the megahertz we had a meter. But you can theoretically actually extend the ambiguity range, into the kilometer or hundreds of kilometer regime. But you can see we got micrometer, sub-micrometer precision in the LiDAR application with this first demonstration. And be aware, these are free running lasers, so they have not been stabilized just because you do it with this polarization duplexing. So these lasers, these mixel lasers are extremely low noise, and that goes all back to the high Q cavity. So this shows you the timing jitter noise. This is the fluctuation on the arrival time of the pulses, or then the fluctuations on the frequency cone position. And when it's a pretty busy slide, but let me just give you a highlight. This is the noise power spectral density as a function of a frequency, how noise, at what frequency fluctuations the noise. If you integrate it from 1 hertz to 10 hertz, the RMS amplitude noise is less than 0.1%. And when you look at timing jitter for free running from 100 hertz to 100 megahertz, you have 127 femtosecond. You can do an active stabilization with the cavity length, easily reduce it to 31 femtosecond, still maintaining really low amplitude noise. So what does this really mean? Why do I say this? This is basically comparable to solid state lasers. So when you have, for example, and use it for dual comb application, 127 femtosecond timing jitter over 100 hertz to 100 megahertz. Basically, the 100 hertz gives you the measurement time. So if you have a pulse repetition rate of 2 gigahertz, the comb lines are spaced by 2 megahertz. In the timing, this is basically 0.5 nanosecond between the pulses. So if you have this 127 femtosecond fluctuation in the arrival time of the pulses, that translates then into a comb line variation of 10 to minus 4. Integrated if you do a measurement over 10 milliseconds, 1 over the 100 hertz. So this is such a small little fluctuations of the comb lines that for most applications, this is sufficiently stable, and that's why you can do all these things rerunning. So we also showed that when we used these femtosecond pulses from a Modlock Bexel chip, we have good stability so that we can stabilize the frequency comb with super continuum generation in a silicon nitride waveguide without any additional external amplification of the signal, and get a stable frequency comb. And that is something, when you actually use a semiconductor, when we wrote our proposal, people argued that this is not possible because the semiconductor, Modlock semiconductor laser will be not low noise enough. But this is basically to emphasize that again, this is because we have a high Q cavity, because we go vertical to the quantum well in the game. So when you look now at the material optimization that we did over the years in the near infrared, I mean, just to give you a little bit of a broader picture, the optical pump VCSEL technology have been extended from the visible to the mid-IR, and the highest power is obtained here on a log scale with over 100 watt CW output power with the indium gallium arsenide gain. Okay, but the semiconductor offers backup engineering and a much larger variety, and it is really impressive to see how relatively high, over 1 watt average output power has been demonstrated over 2 micron, and has been pushed even to the mid-IR with reasonable output power in comparison to other technologies. And when you look at the Sesams, in the near infrared, we mostly have been working with low temperature grown indium gallium arsenide, and that covers a spectral range up to 1.5 micrometer. The benefit that we are having is that we can get the gallium arsenide, aluminum arsenide CBR which are nearly close to lattice match. And we can, by moving into the low temperature MBE growth, we get, first of all, a fast structural absorber, but we also get strain relaxed structure with clean surfaces, which then allows us to push indium gallium arsenide structural absorber all the way to 1.5. So we increase the indium content and therefore the strain, but because we grow it at low temperature, it's actually strain relaxed and the surface is clean. So I've been working on with these low temperature grown seasons ever since I was at Bell Lab. I did then a more careful study of the optical properties of this low temperature grown subtropical absorber, where we optimized the material properties. Because the relevant macroscopic parameters that we need to optimize for the mode locking at what fluence, this is the pulse energy density, at what fluence the subtropical absorber in the reflector is saturating. And we need to know when in the fully saturated regime, where we typically operate, we have a certain modulation depth, which is in the orders of percent, multiple percents. And then we normally have some non-saturable losses, and this we need to minimize to optimize the performance. In addition, we need to get the defects going in these low temperature materials in the right way so that we get a reasonably fast subtropical absorber. So typically for solid state laser with soliton mode locking, we can live up to 50 picoseconds. For the VCSEL, we need faster subtropical absorbers. So the low temperature MBE growth, we did a more detailed study on the properties of these macroscopic parameters for the subtropical absorber. So when you grow gallium arsenide at low temperatures, you introduce mid-gap defect. So you put arsenic at gallium places. So it's arsenic, so-called arsenic antisites. Normally, when you grow that, you have more of these arsenic antisites are neutral. Some of them are positively charged. And actually, these are the good traps. These are the electron traps. If you have actually the neutral antisites, you end up with non-saturable losses with the transition from this state high up into the conduction band, which is not so easily saturated. And that's why you end up with rather high non-saturable losses, which can be as big as the modulation of your subtropical absorber, which is not what you want. So what we realized is when we actually anneal the structure, then these arsenic antisites start to move around and form arsenic precipitate. And these arsenic precipitates are still very good traps, and we reduce the number of neutral arsenic antisites. We also could show if we add beryllium doping, we can also reduce the neutral antisites and have more positively charged arsenic antisites. And with this technique, we were able to reduce the non-saturable losses much smaller than the modulation depths in these low temperature grown gallium arsenide. We saw similar behavior in indium gallium arsenide, even though we didn't do an explicit study on indium gallium arsenide. That is the basic mechanism that helps us to work. So when we move from longer pulses, pico, many hundred femtosecond pulses, to 20-second pulses, then we have significant two-photon absorption in the semiconductor, and that causes a rollover, a so-called inverse subtropical absorber, as a function of incoming fluence on the subtropical absorber, now normalized to the saturation fluence of the subtropical absorber, and you look at the nonlinear reflectivity. You can see without any of these two-photon absorption, you go up here, you have the leftover non-saturable losses on the modulated depth. Now, with the femtosecond pulses, you also get two-photon absorption, which actually then increases the non-saturable losses because electrons get pushed up very high into the conduction band, which are not saturated so easily. So you increase your non-saturable losses, and your effective modulation depth gets reduced. Okay, so this is not good. And we developed a theory which explains this nonlinear response with an additional parameter, F2, which gives you the strength of this two-photon absorption. Again, a macroscopic parameter that we need to optimize. And we could show that the maximum of the nonlinear reflectivity change, where normally the laser is then operating, is given by this equation, which is the square root out of F2. We could also show that the damage of the Sesam is related to the F2. So this is then the design guideline that we want to make F2 as high as possible in comparison to saturation fluence to reduce this effect. So if you do it right, the rollover is at high enough fluences, far above the saturation fluence, so that we also don't have much increase in the non-saturable losses. In addition, for active devices and even for systems where we use more than just one indium gallium arsenide quantum well, we need to start to worry about strain compensation. So the indium gallium arsenide here at around 1 micron is here, so which is basically, when you look at the lattice constant, it's introducing a strain on the gallium arsenide, aluminum arsenide crack mirror. So you can then use different materials and introducing phosphor into it to do the strain compensation. Now, from an optical point of view, it matters what you take, because a large band gap material will have less two-photon absorption. So by actually moving to the quaternary material for the strain compensation, you can substantially reduce the two-photon absorption, which has been helping us even get less than 150 femtosecond pulses for a metal, where of course the two-photon absorption becomes more and more significant. The other thing is the device structure with regards to the field enhancement. When you have your Sesam with the saturable absorber, and here is the DBR, I show here the refractive index profile as a function of the distance looking from the top into the Sesam. So this is only a fraction of the DBR that I'm showing here. And in this case, you have some kind of a saturable absorber, indium gallium arsenide, or in this case, it's a gain mask. And you look at the standing wave profile, because you come in here. And so this is practically 100% reflective with a little bit of saturable absorber. So if you look at the standing wave from 100% reflective, you have a field in intensity enhancement of a factor of 4 when you come in. And inside, if you have a so-called anti-resonance structure, you have a much lower field enhancement. So we did all the early work on with anti-resonance Sesam for the following reason, because when you look at the field enhancement is not very wavelength sensitive, because you want to get short pulses, so you don't want to have a strong wavelength dependence in the saturation of the saturable absorber. And what is even more important, especially in the active structure, is that you get a relative flat group delay dispersion, which is important for keeping the pulse together. For many applications, you want to actually have a low saturation fluence. You can go to a more resonant structure. So here is, of course, the fluence inside is much smaller, so that tends to push up the saturation fluence. If you keep it equally high, you lower the saturation fluence, but then you have a resonance structure. So, you know, the field enhancement is strongly wavelength dependent, and even worse, the group delay dispersion. We can go, for example, in this intermediate design, for example, with top coating, which is anyway good because being a saturable absorber right at the surface is bad for damage. So you have an additional dielectric on top, which passivates the surface and gives you an tunable, adjustable thing of the field enhancement in the saturable absorber. And so you can still get reasonable flat CVD and reasonable flat field enhancement over a probe bandwidth. And this gives you an additional parameter to tune the saturation fluence. Okay, And this all has been then used when we did the mixel integration and the mode locking of the VXL. So you, again, you take the VXL and the Sesam, integrate it into one wafer, and you get the mixel, which then supports this really short cavity. And for a repetition rate of 3 gigahertz, you have a 5 centimeter cavity. When I mode lock this dipole solid state laser, I have significant gain saturation. So I need to make sure that the loss saturation is sooner, faster than the gain. So that means the saturation fluence of the gain needs to be larger than the absorber. If you have used the same material and the same field enhancement, this is not what you get. You don't get the net gain window. So that's why initially, because we use indium gallium arsenide gain, indium gallium arsenide Sesams, so same material, we have to focus more strongly onto the Sesam for and especially for an anti-resonant Sesam to get this condition to get it passively mode locked. But if you want to do the integration, this is not going to be good enough. And so our effort was to demonstrate that even mode locked VXL with practically the same mode size, both on the Sesam and on the VXL, before we could start to work on the integration. One way to do this is to go to a more resonant structure. So, however, if you do that with the quantum well, if you go push it too much into the resonance, actually your modulation becomes too large, because the delta R F sat is actually independent of design. So you would have to very carefully keep this one so that the modulation depth doesn't become too large for the passive mode locking. And also, we figured we should need to move away from the same material. And my expectation was at that time to go to quantum dots. Quantum dots have a lower density of state, so I assume that they have a lower saturation fluence. And so we started working on quantum dot saturable absorber. And the quantum dot saturable absorber have also not the limitation with the delta R times F sat being constant, because you can tune the delta R, the modulation, with the dot density, while the F sat, assuming the dots are the same, remains the same, which is shown here. So by growing different monolayer thickness of the indium arsenide self-assembled quantum dots, we got more or less the same saturation fluence, and we could tune the modulation depth in the saturable absorber. The disappointment that we had is that the saturation fluence was actually rather high. So at that time, we wanted to really demonstrate the first mixel to keep our funding agent happy and continue to get funding. So we pushed the first mixel demonstration into resonance. So this means that we had a higher field enhancement in the quantum dot saturable absorber in comparison to the indium gallium arsenide gain. And we successfully demonstrated passive mode locking with picosecond pulses and 40 milliwatt average power, which made our funding agent happy enough so that they continue to fund us. But we realized that this was a really heroic experiment from the graduate students, because it was really finding the sweet spot on the mixel chip. So we did some more optimizations of the quantum dot Sesams and realized that when we anneal the quantum dot Sesams, which we do anyway in the mixel saturation, then we can, when you look at the saturation fluence here, when we do the different monolayer coverage here, you see that the saturation fluence is rather high. But then by annealing, we can lower the saturation fluence to a level which is acceptable, around 10 microjoule per square centimeter or even below, but only if we grow a maximum level of monolayer. And you can see this is kind of the sweet spot here. So we get sufficient modulation depth because, with this monolayer, we still get about 0.8% modulation and low saturation fluence. And so we went ahead and after this optimization and integrated this quantum dot saturable absorber into the mixel structure in a anti-resonant design, so we don't have the field enhancement in the saturable absorber. And this one worked beautifully. I mean, you could tune the spot size on the mixel and get pretty much the similar result. And this is the explanation is very simple, because the enhancement of the absorber, when you assume a 1% error in the layer thickness, you can see that you don't have a strong wavelength dependence. Whereas here, the error is much more significant and you have a strong wavelength dependence. What is even worse is the group delay dispersion. That one is really bad for the resonance structure and much better for the anti-resonance structure. And I'll tell you then later on how to optimize this further, because you have here units of thousands of femtosecond square. And, for the really short pulses, that is actually too much. This is the result. We got nice output power, over 6 watts of output power at 960 nanometer. The only disappointment was that we had picosecond pulses, not along 30 picosecond pulses. A further investigation of this integrated structure, however, showed that actually, because of the annealing of this quantum dot subgroup absorber, they became slow. This is on a time, the recovery time, over 100 picosecond, and that was not fast enough to get the short pulses. When we did a similar experiment with basically the Sesam Wechsel approach, where we could keep the Sesam unannealed, and we had the Wechsel here, so we could, with the same kind of quantum dot Wechsels, but not annealed, they were fast enough, not so strongly annealed, kind of a compromise, we could get sub-picosecond pulses. So it was clear that we needed something else as quantum dots. And by accident, we stumbled onto a solution. I will talk about further quantum dot subgroup absorber optimization later, because we actually found even a better method than what we have been keep using. But let me go step by step. So we discovered by accident a novel quantum well absorber, which was actually fast, although when you anneal it, extremely robust under annealing, long time annealing. And the thing was that we embed the low temperature grown indium gallium arsenide quantum well absorber, also in low temperature grown barriers, aluminum arsenide barriers. It turned out the defects in these aluminum arsenide barriers were much more robust with regards to annealing. And then we just used this indium gallium arsenide saturable absorber closer to the band edge to get the faster saturation, and in comparison to the gain, and also worked with the field enhancement for other reasons. And when you then look at the advantage, moving to this quantum well saturable absorbers again, we got everything, all the problems that we encountered with the quantum dots that became slow with the integration resolved. The only challenge was that they tended to be more temperature sensitive, so we had to keep the temperature in the design and in the operation more under control, for which we now have a solution. We discovered that 2013, and since then there were actually some more material investigations which actually showed that these defects in aluminum arsenide are rather fixed in their position and cannot be easily moved. And the good news also from a more recent theoretical prediction is that actually in the gallium arsenide, aluminum arsenide superlattice, they found that it is energetically more favorable to get these anti-sites defect, more anti-sites defects than these vacancy in the interstitial defects, which are not so good for saturable absorbers. So we were just lucky, and which was confirmed later on, why we were lucky with these aluminum arsenide low temperature grown barriers. And so by integrating this one, and by putting this whole thing on a heat spreader, and then basically using the saturable absorber still in an anti-resonant design. And when you look carefully here in the game, we also moved the indium gallium arsenide quantum well gain away from the peak of the standing wave for multiple reasons. Actually, you also get a broader gain bandwidth. with the less wavelength sensitive enhancement, and then improved the anti-reflection. So this is still in units of thousand femtosecond square, but it's only a few thousand femtosecond square. So this was good enough to support the first femtosecond fully integrated mixel at 600 with 620 femtosecond, 100 milliwatt average output power. And by just changing the cavity lengths, we could demonstrate with the same mixel chip pulse repetition rate from 5 to 100 gigahertz. So it shows you the average output power and the pulse duration by changing the cavity length and adapting, of course, the output coupler curvature and strength. And we could go all the way to 100 gigahertz with femtosecond pulse duration, basically changing the cavity length from about 29 millimeter to 1.5 millimeter. And, we got watt level operation up to 15 gigahertz and femtosecond operation between 60 gigahertz and 100 gigahertz. And this shows you the result from the 100 gigahertz mixel. And this shows you the mode-locked optical spectrum on a dB scale. Think about it. I mean, this is on a dB scale for a semiconductor laser, which is excellent again because of the high Q cavity. This shows you a picture, which is the mixel chip and the output coupler for this cavity. And we had 127 femtosecond with 570 femtosecond. And when you look at the mode lock frequency comb, you can see we have milliwatt of power in each comb of this mode locked comb, okay, which is important for applications. By further optimizing the structure with flattening out the field enhancement by moving the quantum well gain away from the peak of the standing wave and also getting these absorbers operating faster than the gain, optimizing the group delay dispersion of the whole structure so that it's flat. So now in units of femtosecond square, it's basically below 100 femtosecond square. And by doing that, we could support 100 femtosecond pulses. And we always worked on Sesam and Wetzel mode locking because we had more adjustable parameters. And as soon as we could confirm that our design parameters were actually working, we then did the next step with the mixel, with the full integration. And so we put all the improvement that we learned with strain compensation, with taking large band gap, with no spectral filtering by moving the gain away from the peak, by using a really high quality dielectric top coating to do the flat GDD compensation of the structure. We could also demonstrate 140 femtosecond pulses, and we pushed it at that time to 103 micrometers. This shows you the result. You have to do really careful pulse characterization because sometimes, because it's a high Q cavity, these later go into multi-pulsing, and you want to make sure that you have a fundamental mode locking, one pulse per cavity with really low noise performance. And this is the performance we got out of this mixel at 1 micron, and we used that mixel chip to do the dual comb spectroscopy application and the LiDAR application that I was talking about earlier. So I already mentioned, the disappointment, the early disappointment we had with quantum dots at the Roblox source. I started then a collaboration with Professor Reitmeier, and he had the idea that you can also get very efficient trapping by actually using p-type delta doping next to the quantum dot. So you use high quality quantum dots, which then also have the expected low saturation fluence. And with the additional delta doping, which is modulation doping, which increases the hole density in the quantum dot, so that you have increased radiative recombination, make a fast saturable absorber, you can actually, and they are very stable with regards to annealing. And so for further mixel application, this is the way to go because you get much less temperature sensitivity. Okay. Now let me move to the long wavelengths result that we started actually on the 1st of January 2019, because we got a lot of interest because of our dual home spectroscopy results to push this one to the longer wavelengths for trace gas detection and so on. So I got an ERC advance grant for this one. We started on the 1st of January, and we started a full new growth effort at these long wavelengths, because that needs a significant investment. You have to get the growth, you have to get the characterization, because you cannot work blindly. And so we had an additional grower helping to get us going. It's your Aladdin joint Matthias Golling. This work is also motivated by the really great work from the Fraunhofer Institute in Freiburg, where they compared all the CW sources in the mid-IR wavelength region, 2 micron, all the different sources that there are out there. On a log scale. And you can see that the gallium antimonide-based VCSEL showed great performance up to pretty high wavelengths. It's all based on type 1 VCSEL. And that is basically the motivation. They have not been really working on mode locking. And so we basically set out to do the mode locking, to repeat the success story of the VCSEL at 1 micron and push it into the long wavelength regime. So when you look at the 3.5 material, we still want to stay with 3.5 material. We can then, when we go to the gallium antimonide, we can benefit from this material, structural aluminum antimonide, to get a really good VBR. Then we again increase indium to get to the different wavelengths. Again, we get a lattice mismatch, and we want to use it for active and passive structure. And we want to push it as far as possible into the mid-IR. And so we will explore both type 1 and type 2 structures. And when we started this work, some systems have been demonstrated at 2 micron before, but they have had not the investment in the whole characterization, and that has a real effect, as I can show you here. So, for example, when you look at the dye-pumped solid-state lasers that have been mode locked with Sesams, then the chromium sulfide is basically the Ti-sapphire laser for the long wavelengths, very broad gain bandwidth, and there has been a lot of mode locking, passive mode locking of this laser material, mostly with Care lens mode locking, graphene, and also with Sesams, okay, with average power and repetition rate. Our results with the improved Sesams that we did with 2.4 micrometer type 1 Sesam shown here. So this is at about 250 megahertz, and most recently also at 2 gigahertz, which just shows you what you can do if you invest into the proper development. So this just shows you the cavity of the 2 gigahertz cavity, where you have this Sesam, and then you use the YAG crystal for negative dispersion, and you have the cell phase modulation in the chromium zinc sulfide. So you have, again, soliton mode locking, which actually also requires the requirement on the saturable absorber. So it's not a hard test on the saturable absorber, because we got it going with both type 1 and type 2 Sesam, which is interesting. The type 2 Sesam would not work in the VCSEL. But it was really nice that we could show this improvement, and that, again, the mode locking is really done by soliton mode locking, which you can see. This is the average power on the left, the pulse duration on the right as a function of pump power. And you can see when you get into the regime of CW mode locking, the pulse duration scales here correctly according to soliton formation, and the pulses are transform limited. So this is the first really positive result when you do the things right. And for this, to get to that point, we had to build up the full characterization, Sesam characterization, which we had in the near infrared. So we do the design, we then do the characterization before we do the laser work. And without that, you're kind of acting blindly. And so we built up full characterization with commercial OPO that gave us the femtosecond femtosecond pulses from 1.7 to 4 micrometer. And the optics that we used in the setup cover the range of 1.9 to 3 micrometer. And we could ultimately, anybody who has worked in the near infrared and moving to the mid IR, things are not so totally trivial. And it was the really great effort of 2 new graduate students who took our know-how from the near IR, pushed it into the mid IR, and could show an accuracy over 4 orders of magnitude, which is very similar to the near IR, which you need because we only looking for a few percent of modulation depth, right? And we first built 2-micron indium gallium antimony Sesams, which are type 1. So it's the same thing that we did in indium gallium arsenide. We again grew a higher reflecting mirror, which is 20 pair, and then we had this quantum well for the satellite absorber. We did 3 Sesams with different number of quantum wells from 2, 3, and 4, and we could show in the measurement that indeed the modulation depth gets up when you put more. It's an anti-resonant design, so the saturation fluence is really low, which is nice. And what is really important here, the non-saturable losses are a small fraction of what is the modulation depth, which is really essential for mode locking VCSEL. And so this shows you the high accuracy measurement using the 100 femtosecond pulses, which also then gives you this rollover. And the pump probe gives you the recovery time. So this is one thing, you don't have to work very hard at this material type 1 that you get a fast subtotal absorber. So we got between 15 and 30 picosecond recovery time, which is actually ideal for the VCSEL modulation. We also giving these Sesams to Professor Clara Saracena, who is using it to Sesam mode lock a holmium YAG laser. We also started a network at 2.4 micrometer, where we also explored the type 2 option, okay, but initially as a subtotal absorber. So again, in the 2.4 micrometer type 1, we had 3 indium gallium antimony quantum well absorber layer still in an anti-resonant, this is the field enhancement anti-resonant configuration. But then we also did a type 2 system, also anti-resonant, but the type 2 we need, of course, to get the sufficient modulation depths. We needed many more of this W structure to get the sufficient modulation depth, which is shown here. And when we did the characterization, nonlinear reflectivity, and the pump probe, you can see exactly what you would expect. First of all, that you have a fast subtotal absorber with the type 1, which comes for free in the long wavelength regime. And with the type 2, you get the long lifetime. And this is exactly what you want for the active region. So we did the saturation fluence measurements and so on, and we got a modulation depth of 5% in the type 2. The type 1 was 1.6. These are our first devices in this wavelength regime with saturation fluence. We still need to fully understand the numbers. And basically, this looked very promising. We actually used both Sesams for the mode locking because even with this slow subtotal absorber, we still could do soliton mode locking because the pulse shaping in the solid state laser is not done by the fast subtotal absorber. It's the stabilization, but it was definitely much less stable with the type 2 Sesam. And, but of course, the type 2 Sesam has less strain. So let me conclude. This is an overview of the results in the near infrared. So based on solid state lasers and based green is everything on VCSEL and Sesam mode locked VCSEL and VCSEL as a function of pulse duration. So you can see in comparison to all the competing technology, we're very similar with the semiconductor lasers. The only benefit is the Ti-sapphire laser. To go to the Ti-sapphire laser if you really want to get the extremely short pulses. But you pay a high price because it's an expensive laser. When you look at the pulse energy, you can see that we get comparable pulse energy as a function of repetition rate. So average power argument is not there, and you get this really good performance with the optical pump semiconductor. And what makes the mix also interesting is you have a very simple cavity design. You get dual comb mode lock, also in a very simple kind, and you don't have to stabilize the laser at all for most dual comb applications. So I think we have now a laser technology that is actually ready to be picked up for real world application. And I hope there will be an application where people get excited about it to invest the development into a real product. So our efforts right now is focused only on the mid-IR because we have the funding in this regime and we are motivated by the prior CW results by our colleagues from Fraunhofer Institute. And when you look at our first results on the Sesam, we now work with 2 micrometer VCSEL also on the type 1, looking to do the Sesam mode locking and to ultimately do the integration on the VCSEL and do the dual com VCSEL demonstration. Meanwhile, we make these systems available for dye-pump solid-state laser mode locking where we are not want to do it on our own. And the 2.4 is interesting for us to go in parallel because in that wavelength regime, it makes sense to really go also and explore the type 2, both for Sesam and gain application. And of course, the type 2 gives you right away the long carrier lifetime. So for the active region, it's clear that you want to move into the type 2 VCSEL, which also gives you the potential to push this technology much further into the mid-IR than it has been done so far. So this is basically work in progress, and I'm, stay tuned. I hope I can tell more results very soon. And, we all suffered from partial lab shutdown and home office. And, I can say that I finally finished a 25-year-old project and finished textbook on ultrafast lasers with all the laser physics that goes into it to produce a stable pulses from optically pumped solid-state lasers. And I actually submitted now this textbook end of April to Springer, and hopefully this will be published by the end of 2021.